Okay, so today I will be introducing parsley to all of you. As we all know, parsley is mainly used in cooking ingredients, but actually parsley has a lot of many uses. Parsley is rich of source of volatile essential oils, polyphenols, and secondary metabolites that serve as a natural antioxidants and antimicrobial agents. Okay, so the scientific name of a parsley is Petroselinum crispum, and the kingdom of a parsley is obviously Plantae, which is plants. And parsley came from a family is named as Apiaceae, formerly is Umbelliferae. So the genus of a parsley is Petroselinum, and the species is P. crispum. The genus and the species, we can get it from the scientific name. So the native habitat of a parsley is Mediterranean nature, which is parsley live in the wild environments. So parsley is thrive in rocky crevice cliff and stone walls throughout the southern Europe and parts of North America. The other fact about the growth of a parsley is parsley loves the mild, wet winters and warm sunny summers because it helps them to grow faster. But parsley isn't a fan of extreme tropical heats and desert because it struggles to peak of a hot summer. For the global distribution, parsley has been naturalized, which means the parsley grow wild on its own in many parts of the world. So for the biosynthesis of a parsley, the chemical in the parsley itself, profile of the plant changes significantly between the first year, which is the leaf production, and the second year, the seed production. So the concentration of the essential oils in the seed is much higher in the leaf. So move on to the next slide, which is parsley and chemistry. What is the chemistry in a parsley? So basically, chemistry research in a parsley has often focused on its bioactive compounds, which is phenylpropanoids and the flavonoids that are studied for the potential in pharmacology and food preservation. So there are three chemical characteristics in a parsley. So the first one is the essential oil composition. So the characteristic aroma in the parsley is dominated by two phenylpropanoids, which is ethyl and myristicin. And the second point is about the flavor molecules. This is basically focused on the green scent on the parsley, which is largely due to 1,3,8-P-methyl monoterpene that act as a chemical signature for the plant itself. So that's why parsley has those grassy with spicy, earthy, and sometimes faintly fruity scents. So let's wrap up on the third and the last point of the chemical characteristic in the parsley, which is the flavonoids. So parsley contains of high level of epizinin, which is a yellow crystalline solid that often used in studies regarding the cellular oxidative stress.
Traditionally, parsley has been widely used for its medicinal properties. One of the main traditional uses of parsley is to aid digestion. It has been used to reduce bloating and stomach discomfort. Parsley is also known as a natural diuretic. In traditional medicine, it was used to help increase urine production, which supports kidney and urinary tract health by removing excess water from the body. In addition, parsley has anti-inflammatory properties. Traditional healers use parsley to help reduce inflammation and relieve minor pain, especially related to joints. These medicinal effects are believed to be caused by active organic compounds, such as flavonoids and phenolic compounds found in parsley. Therefore, parsley is not only used as a culinary herb, but also plays an important role in traditional and medicinal practices. These traditional uses are supported by the presence of bioactive organic compounds, which will be further discussed in the chemical compounds section.
Based on the chemical structures shown, these compounds are known as epigeny and luteolin. From the structures, several functional groups and homologous series can be identified. First, both epigeny and luteolin contain phenyl groups, which are OH groups attached directly to aromatic rings. The functional group for phenol is hydroxyl. Next, both compounds contain aromatic rings. The functional group is benzyl rings that place in epigeny and luteolin in the aromatic homologous series. Both epigeny and luteolin also have a ketone group shown by the C double O bond in the structure. This belongs to the ketone homologous series and the functional group is carbonyl. In addition, an ether group is also present in both compounds. The COC linkage connecting the rings indicates an ether, placing it in the ether homologous series, and the functional group is alkoxide. Lastly, C double bond C are present in the rings of both compounds, showing features of the alkene homologous series, and the functional group is carbon-carbon double bond. Epigeny and luteolin share similar functional groups, with luteolin having an additional hydroxy groups which enhance its chemical reactivity.
Let's take a closer look at epiol, a naturally occurring compound found in parsley oil. First, we have the ether group, especially an alkoxide, which contributes to its solubility and reactivity. Then there are allyl motif. This means it has both an allyl group and penyl ring, a combination often seen in bioactive phytochemical. And finally, the alkene group, a carbon-carbon double bond, which play a role in its chemical behavior and potential interaction. Next, we have coumarin. First, it is aromatic thanks to its benzene ring, which contribute to its stability and scent profile. It contains an ester group, especially carboxyalkoxy, which is a key to its sweet-smelling nature. The molecule also includes an alkene, a carbon-carbon double bond that adds reactivity, and finally the ether group and alkoxide that influence its solubility and interaction with other compounds. This compound is called myristicin, which is a natural organic compound commonly found in nutmeg or parsley. Based on its chemical structure, myristicin belongs to several homologous series. First, it contains an aromatic ring, especially a benzene ring, which gives the compound stability. Next, the structure shows a carbon-carbon double bond, so it is also classified as alkene. Myristicin also has an ether functional group shown by the alkoxy group attached to the benzene ring. Additionally, it belongs to the alkylbenzene family because the benzene ring is substituted in an alkali side chain. Lastly, it is classified as a phenylpropanoid, which means it has a benzene ring attached to three carbon side chains. These structural features explain the chemical property and biological activity of myristicin.